Hello? Okay. So, oh, thanks for coming after the dinner. And I actually feel like full of energy somehow today, so I assume that everyone is feeling the same. So, so what I'm going to talk about is some relation between S-matrix and the CFT correlators, and that's work in progress with Miguel Palos and both Fan Rees and Shan Zhao, both and the last two are in the audience. And the goal of my talk is to learn about S-matrix in flat space, especially like analyticity, crossing, and in particular, those like a two-question analyticity and crossing are kind of like, I guess, like a more non-trivial if you start talking about higher point functions from conformal field theory. But in my talk, I'm mainly focused on 4-point functions, but in the future, it will be nice if one can generalize these ideas to higher point functions. So let me explain what is the relation between the flat space S matrix and the CFT correlators. Of course, they are not the same, but the idea is to use the ADS CFT correspondence. So thanks to the ADS CFT correspondence, you can map the correlation functions in CFT in D dimensions to the something like a scattering amplitudes in ADS in D+1 dimensions. And the idea is to take a limit in which the ADS spacetime becomes a flat spacetime, and then you can relate the CFT correlators with the scattering amplitudes in Minkowski spacetime. So, but before I explain how this can work, let me explain why I want to do this. So the reason why I want to do this is because actually we know more about CFT rather than scattering amplitudes. Of course, this might sound a bit counterintuitive because if you learn quantum field theory in grad school, then you first learn how to compute the scattering amplitudes in Minkowski spacetime, and the CFT appears much later. But this claim will will be a bit easier to understand if you, for example, try to understand the crossing symmetry rigorously in S matrix in flat space or in the CFT in the correlators in CFT. So if you really want to discuss the crossing symmetry in flat spacetime, then I don't know how many people try to go through that like a proof, but it's actually very technical. You need to use edge of the wedge theorem. And well, I don't even know what is the correct name, but it's complicated. And on the other hand, the crossing symmetry of CFT is more or less easier to understand. We know when OP converges, and then if the two OP if there is a overlapping region of two OP convergence, then you can just argue that there is a crossing symmetry. And related fact is that analyticity of the CFT, we know actually more about analyticity of the CFT correlators than the analyticity of the scattering amplitudes. And furthermore, thanks to the recent development, we actually know a lot about Regge trajectory of the CFT correlators. In particular, thanks to the work by Simon Caron-Keogh and also the work by David Simons-Duffin and Peter Kravchuk, we actually can write down some operator that's responsible for the entire Regge trajectory and then directly study the Regge trajectory. And furthermore, although this is not really done yet, but there is a hope. Well, it's possible that on the CFT side, you can write down or try to analyze the double dispersion relation, whereas things like that is a bit hard on the flat space scattering flat space scattering amplitude. Okay.
This would be this quadruple.
Yeah, quadruple discontinuity. Yes. So this is the basic reason why I want to study scattering amplitudes from the CFT correlators. And let me just briefly review how this tool works, mainly ADS CFT works. So in the ADS CFT, there is a correspondence between CFT correlators and quantities in ADS. So on the CFT side, the basic observable is, of course, the correlation function of some local operators. And roughly speaking, this gets mapped to some asymptotic state, or what becomes the asymptotic states in the flat space limit in ADS spacetime. So pictorially, if you insert some operator O at the boundary of ADS, then this operator O acts as a source and then creates a particle inside. And for instance, if you consider the stress energy tensor in CFT, it is known that this acts as a source for the G mu nu, which is graviton in ADS. And if you consider more general operators, there is a basically relation between the dimension, conformal dimension of the operator, and the mass of the particle in ADS. And the relation is given by this formula, where D is the dimension of the CFT, and M is the mass of the particle in ADS, and R is the radius of ADS. And there is also, of course, some relation between correlation functions. For example, if you consider the three-point function, that's going to be basically three-point amplitude in ADS spacetime. So this is basically how the standard ADS CFT works. But in my talk, I basically consider quantum field theory in ADS rather than like a quantum gravity in ADS. So today, I consider theory with no gravity. Furthermore, I focus on theories of massive particles. So all the particles living in ADS are massive. So basically, this means that I don't have this on the ADS side, which means that I don't have this T mu nu on the conformal field theory side. So of course, like a series without like a stress energy tensor is not a bit like unusual, but you can actually construct such a series, for example, by considering some like a starting from like a long-range spin chain and taking the continuum limit. So because of this reason, some people call this CT rather than CFT because it's not the standard CFT, and the typically standard CFT definition includes the existence of the stress energy tensor. And so what I'm going to study should be called something like CT rigid ADS correspondence. I put.
Do you have a generator, some operator, a generator format?
Yeah, I assume that there is a generator, which.
They are global and not local.
Right, exactly. You don't have a current, but you have a charge. All right, so this is a setup that I want to analyze. And basically, in this setup, in particular, if you just look at this formula, you can see that flat space limit, which basically corresponds to taking our ADS radius to be infinity, basically amounts to taking delta, which is the dimension of the CFT operator, to be infinite. So I'm going to study some conformal theory whose operator all the operators have very large dimensions. Okay, so this is the limit that I'm going to discuss today. But before discussing what we are analyzing, let me just mention several previous works, which also analyze this kind of limit. Is there any questions so far? Sorry?
Some of it analysis and things in CFT, but not from the local.
Well, Well, not everything comes from like a, well, you don't need to have a stress energy tensor to make claim about some of the properties of analyticity. Okay, so all right, so let's see what I'm going to. So let me just review the previous proposals. So one proposal which probably most people are familiar with is the proposal which uses what's called mailing amplitude. So the idea is as follows. So the idea is to write down CFT correlator. Well, let's just focus on 4-point function, and then express it as some kind of mailing integrals, mailing transformation. And so you have some factors which involve gamma function, and you have like MST, and then ZZ bar to S and S plus T. So the details are not really important, but the point is that Z and Z bar are basically the conformal cross ratio, which parameterizes the position of these operators. And these S and T are integration variables. So the idea is that if you do this integration, then you get back to the correlator. And this proposal was basically made by Joao. And the idea is that once you succeeded in writing the correlator in this way, then roughly speaking, this part becomes amplitude in flat space in the flat space limit. So this is kind of nice because you can directly see something that looks like amplitudes from the CFT correlator, but there are also some limitations. So the good point here is that conceptually, nice, but there are also some limitations. The first limitation is that, so let's call this G, this correlator G. It's not always easy to start from the correlator and get the mailing amplitudes. Because here I wrote down the correlator in terms of mailing amplitude, but in order to really know what this M is, you actually need to do some inverse mailing transformation to this correlator G. And that basically involves doing some integral of G with some extra power factors. And first of all, this basically involves various kinematics, and you need to analyze various kinematics separately. And also there can be some singularities when two points collide, because there is always OP singularity when two operators are close to each other. So of course, it will be probably possible to overcome this difficulty and then try to make it precise. But in any case, you need to do some integrals in order to get the mailing amplitude starting from the CFT correlator. And another.
Could it be that if you are only interested in flat space limits, how these integrals are taking place instead of points?
Yeah, that's probably true, but yeah. But yeah, let me postpone that question to later, because that will become clear later probably. But another small unsatisfactory point is that this MST actually have accumulation points, accumulation of poles. Of course, this is not super bad, but it's not sometimes not very desirable. So I'm not going to explain why it has accumulation points of poles, but it is known that MST should have accumulation points of poles. All right, so, and finally, at least at this point, analytic property of MST is not entirely clear. There are some works to be done to really understand what is the analytic property of MST. All right, so because of these reasons, today I would like to take a flat space limit directly at the level of the CFT correlators. So because of these reasons, I want to take the flat space limit directly in position space. Okay.
So why is it not clear what the analyticity properties of n are? I mean, isn't it just that you can only have a simple pole?
But it's a bit hard. Well, first of all, there is also accumulation points of simple poles, and which makes it a bit uglier. And also, if you really want to show, for example, what is the asymptotic property of, asymptotic behavior of MST, then you need to do Milli amplitude, yeah, Milli amplitude.
Can I ask just
Yeah.
about the status of this procedure? It exists both for massless and massless particles.
Okay, that's what I'm going to write. But before explaining what we are going to do, but let me just write one table which summarizes the status. So there are several works before us about the flat space limit, and then some of them use Milli amplitude, and some of them use the position space or momentum space correlators. So I believe that it was first proposed by Joao how to use the Milli amplitude to extract the massless amplitudes in flat space. And later, there was a paper by Miguel Palos. Okay, sorry. Yeah, people, mainly including the organizers of the conference. So there was a proposal by these people, Miguel Palos, Penedones, Jonathan Toledo, both Van Ries, and Pedro Viela, most importantly. And they made a proposal of how to get the massive amplitude from the Milli amplitude. And in terms of the position space, there was a paper by Okuda and Penedones, which discussed how to get the massless amplitudes starting from the position space. And there is also work by Duvosky, Gobenko, and these three people, which is mainly about ADS2, but they made an explicit proposal about how to get the massive amplitudes from the position space. And there is also a paper by Elliott, which kind of discusses both massive and massless cases. And what I'm going to focus is basically this part, and then try to make this proposal a bit more precise so that we can really ask the questions about analyticity. Okay? So yeah, I only have 10 minutes left, but let me try to, sorry. Okay, yeah, but anyway, yeah. I probably don't need much more, but. So now I'm going to explain what is the what is the stuff that we are discussing. So let me first start from a very intuitive picture, intuitive explanation about how this idea of getting the massive amplitude starting from the position space can work. But this intuitive explanation is actually wrong. But nevertheless, let me explain this because this gives you some idea what's going on. Explanation. So the idea is that, as I said, the flat space limit corresponds to taking delta to be very large, which on the ADS side, which corresponds to taking the product of mass of the particle times radius of ADS to be very large. And this basically corresponds to taking the limit in which the Compton wavelength of the particle becomes much, much smaller than the size of ADS. And in this, because Compton wavelength is very small, we expect that in this limit, particles are very localized and then travel along the geodesics. So basically, if I were to draw a picture, let's say I have boundary of ADS here and insert some operator 1, 2, 3, 4, then so each operator emits some particle which is very much localized and travel along the geodesic. And then they are not interacting with each other until they meet some point inside the ADS, which is this a region is very, very small as compared to the ADS radius. This is a very intuitive picture what we expect, about what we expect in this limit. And this point can be basically determined by analyzing the saddle point equation. So what I mean by this is that to determine this point, where this point is, you just need to consider product of propagators. So these, okay, I'm using what's called the embedding formalism, but the detail again doesn't matter. And I'm just going to explain the meaning of these objects. So what I'm doing here is that I'm basically integrating over the position inside ADS. And integrand consists of product of 4 pieces. And each piece basically corresponds to a propagator, which connects the boundary point Pi to the bulk point X. So you can think of each object as an analog of E to IPX in flat space. So this is the analog of the.
So what kind of interaction do you have in the bulk?
Okay, so the interaction basically changes some order 1 pieces.
So why you have 2, 1, and 2?
Okay, yeah, that's precisely the point that I'm going to get. But yeah. So, but let me just proceed with this a wrong but intuitive explanation. Then in the limit, in the flat space limit, you can see that this is a product of things with very large exponent. So you expect that you can basically determine where this X is by computing the saddle point equation. So if you solve the saddle point equation, then you can basically determine how the geodesic get connected at one point in space-time. And if you have this picture, then once you have determined the saddle point, then you can just look closely around this point. Then if you look closely around this point, you see that these lines are coming from some direction and then meeting at a point. And because this region is very tiny, you can approximate this region by the flat space. And each particle is coming from some, basically saddle point determines the direction from which the particles are coming in. And these vectors and i's can be read off by solving the saddle point equation. And once you read off these vector and i's, then you can basically read off the momenta of the particle by taking this vector and then multiplying delta I, because we know that the mass is basically given by delta. So we basically put a delta I here. And we also need to divide by R. And then if you carefully work out the signature, then you discover that there is some I here. So this is basically this gives you basically the map between the CFT correlators and the moment of the particle in the flat space limit. So how this works more precisely, like so by solving this saddle point equation, you can determine x as a function of the insertion points of the operator. And from that, you can read off ends. And then from that, you can read off the moment of the particle. OK. So right now, yeah, I'm in the Euclidean signature. All right, so
Where do you get I from? For a Euclidean to I?
yeah, so that's related to the fact that like a k square must be like a minus m square in the signature that I'm using. OK, so this already gives you some relation, as I said, between the CFT correlator and the amplitude. So this basically like suggests that CFT correlator is given by some leg factors, which basically comes from this like a propagation of the particle from the boundary to this point times flat space amplitude. And secondly, by working out those relations and solving the saddle point equation, you can actually relate the position of the operator insertion in CFT and the Mandelstam variable in flat space scattering amplitude. In particular, if you consider 4-point function of identical operator with dimension delta, then you can explicitly write down the relation between Mandelstam variables and CFT correlator, and the relation is given by this. So S is given by 4m squared plus something like this. I'm going to explain what these rows are. And T is given by minus 4m squared, 1 plus square root rho rho bar over square root rho minus square root of rho bar square. And then, yeah, there is some analogous expression for U as well. So what is this rho? So this rho is what's called rho coordinate for the CFT correlator. And so the rho coordinate is defined by mapping the position of the operator by using the conformal symmetry, and by mapping operator 3 to the position +1 and operator 4 to be the position -1. And then you parameterize the position of the remaining 2 operator in the complex plane by like this. So rho is the complex number, which basically parameterizes the kinematics of these like 4-point functions. And what is further nice about this relation is that from this STU relation, you can also read off the scattering angle. And the scattering angle, theta, is precisely like an argument of rho. So this scattering angle precisely is mapped to the angle in the rho coordinate. OK, so this gives you some nice relation between CFT correlator and amplitude, and also like it gives a mapping between the Mandelstam variables and then CFT correlate, the cross ratios. Furthermore, by looking at this relation, you can see like what kind of kinematics in CFT side is mapped to the kinematics of the flat space amplitudes. And you can, for example, check that the Regge limit of the CFT correlator is mapped to the Regge limit of the flat space amplitude, and OPE limit is basically mapped to some S, this limit in which basically like you are near the threshold and in the non-relativistic regime. And another interesting limit is that it's what's called double light cone limit, for which a lot of progress has been made from analytic conformal bootstrap, light cone limit. And this limit is mapped to slightly weird limit, which is S is 4m squared, T is minus 4m squared, and U is 4m squared. From the flat space amplitude point of view, this is a bit weird limit, but given the fact that there have been a lot of progress on the CFT side, it might be interesting to look at this limit also in the flat space scattering amplitude. Yeah, crossing is basically mapped to the crossing, yeah. So now I need to tell you why this is wrong. So originally, rho and rho bar are complex conjugate, but then you can analytically continue. Well, if you believe in this relation.
For example, if I want to go to large energies to S.
Yeah, that's the point. If you want to go to the large energy in S, then you need to go to like basically Lorentzian kinematics of the CFT. So why this is wrong? So in order to understand why this is wrong, then let me just mention well-known puzzle in geometry, which is to like determine the configuration which connects 4 points on the square with minimal distance. So you might think that like if you want to connect these 4 points on in the square with minimal distance, then maybe the shortest way to connect all 4 points is to put a point in the middle and then connect it like this. But this is actually not true. And what gives you the minimal distance is something like this. So I guess this is a kind of famous thing, but like this is one example of symmetry breaking. Although the initial problem had like a Z4 symmetry, but like the correct answer kind of spontaneously breaks the symmetry. So, and something like this is indeed happening in what I just said. So I was assuming that here that like all 4 points gets connected by a single point in ADS. But typically, if you work in the Euclidean kinematics, then there are other configurations in which points gets connected like this. So there is some particle exchange in the middle. And typically, this is actually more dominant as compared to this configuration. And actually, in our case, it's even worse because nobody told us that all points should be connected. So you can actually just connect 2 points pairwise, and this is typically like has a much smaller action as compared to this one. So this actually dominates the configuration. So this is basically telling us that what I just said doesn't work.
I mean, if you look at the full correlator, or if you look at the connected correlator, then...
Yeah, okay, you might say that like if you look at the connected correlator, you can eliminate this one, but still there is typically something like this. So this basically doesn't work, but the important point is that when I was drawing this picture, I was always discussing the Euclidean kinematics. But if you start looking at Lorentzian kinematics, there is one limit in which what I just said should work. So this is what's called bulk point limit. So essentially, the bulk point limit is as follows. So you consider global ADS spacetime, and this is really like a Lorentzian cylinder, and then put operator 1 and 2 here in the past, and then put operator 3 and 4 in the future, so that the time separation is given by pi. Well, pi times r, actually. And in this particular configuration, there is a point inside the ADS which is light-like separated from all the other points. So in this case, basically, the geodesic distance between the points in ADS and the points on the boundary is basically 0 because it's light-like separated. So it doesn't cost any action. On the other hand, if I were to draw something like this here, then I have to connect points using the space-like geodesics. So this is always suppressed as compared to like what I really want to get. So this is basically suggesting that at least in this limit, what I just said should work. So in this limit, things should work. So by combining two intuitions, and this is basically telling us that in some kinematics, this idea of taking the flat space limit directly in the position space should work. But in some other kinematics, especially in the Euclidean kinematics, things do not work. And let me just end by a brief discussion of when it can work. So to analyze when it works, we can start from like anything that we believe in. And you could also, well, in principle, you can also start from the Mealy amplitude, but at this point, I don't have much faith in Mealy amplitudes, so I would like to start with something else. And that something else is what's called Euclidean, what some people call Euclidean inversion formula, or maybe I should call it conformal partial wave. And so this is basically the representation of the CFT correlator as some integral. So this integral seems a little bit similar, but as the Mealy amplitude expression, but this formula, I think, is more established. And the idea is to express the CFT correlator as an integral of like a conformal dimension, which is along what's called principal series. And then you have some function C delta J, and then conformal block, which is a function of rho and rho bar. So this is basically just rewriting of the usual conformal block expansion. And this C delta J has poles on the real axis, and the integration is along the imaginary axis. And if you close the contour by picking up poles, then basically the residue of each pole is given by the 3-point function square, and then you reproduce the usual CFT OP expansion. And so I would like to start from this and then take the flat space limit. And when you take this flat space limit, taking the flat space limit of the conformal block is easy because we know what the asymptotics, what is the conformal block. And roughly speaking, if you take the flat space limit, this behaves like a rho bar to some power, which is proportional to delta. But in order to analyze the flat space limit, I also need to know how this C delta J behaves. And for this, I need to make some assumptions. And the assumption is that basically, as I said, C delta J, when you pick the poles, that gives you the 3-point function. And if you have a local theory in ADS, then this 3-point function is basically given again by some product of leg factor times order 1 number, which is the coupling constant. And if you work it out, then you see that this basically should behave something like, again, exponential to some power times delta. So this you can just like read it off from the Witten diagram computation, ADS computation. So I assume that this C delta J has this behavior. So let me just write it explicitly. So the assumption I'm making is that delta is always larger, much larger than 1, and this C delta J has specific exponential property. And in the case of 1D CFT, you can actually almost prove the second property starting from the first property, as was discussed by Miguel Palos and Emil Mozak. But in higher dimension, we don't know how to prove this one starting from this one. So at this point, I just assume that these two properties, I just assume these two properties to take the flat space limit.
When you say property 2, you say with the fixed exponent.
Yeah, fixed exponent. Yes, fixed exponent. Yeah, I know what the exponent is. And once you have this expression, then again you can see that everything is comes with very large exponent. So you can basically take the saddle point over this expression. And if you take the saddle point, something, okay, I'm really using 45 minutes, sorry, but if you take the saddle point limit, then something nice or something interesting happens. So as I said, so the integral is along the C delta J plane. So let me just find. And originally, the integration contour is somewhere here. So this is like a principal series contour. And there are a series of poles on the real axis, which corresponds to physical operators. And in particular, there is identity operator here, and there is some other operator, light operator here. And then we expect there should be some like a series operator, which corresponds to two particle state in the flat space limit. So this is like a 2 times delta external guy. Yeah, that's true. But okay, so okay, let's assume that we deform the contour a little bit so that identity is on this side, because I want to pick the identity. We need to pick the identity contribution. Right. And then let's recall the relation between S and rho bar. So, and what I'm going to do is to start from this expression and then analytically continue rho bar so that I have some extra phase here. So now this relation becomes something like this. So now I have like a absolute value of rho bar's square root, and then there is some phase. And alpha equals 0 corresponds to Euclidean kinematics. And alpha equals pi corresponds to Lorentzian kinematics. And for intermediate value of alpha, it's some complex kinematics of CFT. And with this, we can just like try to solve the saddle point equation and see where the saddle point is. And if you do so, first, if you start from alpha equals 0, then you discover that the saddle point is somewhere here. And the steepest descent contour is in this direction. But as you can see, in order to reach this saddle point, you actually need to shift the contour in this way. This means that you are picking up poles here. So the real contribution in the flat space limit is given by a sum of the terms. One is coming from the saddle point, and the others are coming from the poles. But the point here is that this is the steepest descent contour. So if I were to draw a steepest ascent contour, it goes like this, which basically means that the value here is much smaller than the value here. So which basically means that this saddle point is subdominant. And if you work out what you get in this from this and from this, then you see that this saddle point contribution basically reproduces what we expect. So essentially, the correct scaling to get the flat space amplitudes, whereas this one basically blows up if you want to take the flat space limit. So this is another explanation why the flat space limit doesn't work in the Euclidean kinematics.
What is the threshold? Like
So it's basically like, yeah, I can look it up later, but I forgot. But it almost never works because of the identity operator. But as you change, as you go to the Lorentzian kinematics, then this saddle point changes a little bit, changes the steepest descent contour changes like this. And in the Lorentzian kinematics, it goes like this. And correspondingly, the saddle point moves like this. And in the Lorentzian kinematics, then you can see, you can also draw a steepest ascent contour, and which goes like this. So in the Lorentzian kinematics, well, we still need to pick a pose, but this analysis basically tells you that maybe in some regions, this saddle point contribution can become larger than the contribution from the pole. And if you work it out, then you discover that the things will work out nicely if S is larger than M squared. And so this is basically the constraint that we obtain from this analysis, and for which we expect things to work out. And so this is not the end of the story, because so far I was discussing essentially what happens to each summand in this a sum over J. So you still need to ask whether this sum over J converges or not. So that we are trying to understand it right now, but at least if you just look at the partial wave, then this is one constraint coming from the analysis. And basically, I should stop, I think, because I went over time.
Maybe a comment?
Yeah.
If you have the S greater than 8m squared, then it seems to work, but we know you also sort of know what causes the divergence.
Right, right.
So you might just
Subtract, you mean, yeah.
Seems, at least in the simple cases, we know it very well. Whether we can find the general theory of what causes these divergences. But then you analytically continue to S smaller?
You mean once you take the limit, then it might be possible. But then it becomes a bit hard to say something about analytic properties.
This sum over spin, doesn't it then become the sum over spin of partial waves?
Yeah.
So this formula would work like you get a flat space limit, partial wave
Yeah.
by partial wave.
Yeah.
I mean, that space the analyticity is just a choice. So you choose the cut and in particular weight to analytically continue, so you don't have to write this here, but then you have them in the next series. I don't know, there is some
But, well, there is always branch points, no? The position of the cuts you can choose, but.
Yeah, you like to choose
Yeah.
the cut, and but then you say I'm going to continue this way so that it's analytic and can pass to the strong series. And then when I cross that series, I get poles or something. But I think you have a choice also analytically continue from the real line, the typical line to the complex plane in flat space.
Mm-hmm.
You should have some choice here.
Well. Okay, so then I'll leave it to your talk.
You said that you had to assume this exponential behavior of the C delta J. So if you start from the inversion formula, C delta